Welcome back. Wow, everyone is really excited to be back. This is great. This is really good. This is good. I think actually 2/3 of the class is here, which is nice to see. It's the day after spring break. Very cool. Everyone have a good spring break? No? Yeah? Yeah? Okay? Just okay?
I went to both of the basketball tournaments. It was kind of sad.
Fair enough. They're in the invitational. What are you going to do? It's all right. Everyone's okay, fair enough. Okay, welcome to Lecture 14. Today, I'm not going to talk about iPhones at all. Not once. I'm not going to talk about iOS. I'm not going to talk about Apple. We are going to talk about microcontrollers, which means we're going to talk about Arduino. So, everybody's worked with Arduino before? Is that right? No. How many people have worked with Arduino before? Or any microcontroller? Well, I thought everybody raised their hand first asked this at the beginning of the semester. Okay, interesting. Fair enough. Okay, so today what I'm going to do is go over all of the basics of working with microcontrollers. See, there's the other third of the class. We're doing all right. So I'm going to go over all of the basics of working with this. We're essentially going to go through a bunch of C code and a bunch of looking at the data sheet for this microcontroller to see how to program on it. Okay? So we're going to take a nice, deep, long breath because this will be related to the next assignment that's due after our facial recognition. So we're essentially going to communicate with Bluetooth to the Arduino, and I'm going to have you do some interesting things with this and communicate it back to the phone so we can do some sensing. And I have a feeling a lot of final projects will be built around, maybe you don't want to do a lot of the sensing on the phone. Maybe you want to do some of it on the microcontroller or more than one microcontroller so that you can kind of a distributed array that you're connecting to, right? So there's some fun and cool things that you can do with that. So course logistics. Grades for A3, they've been up for most of the break. A4s due this Friday. How many people have started A4? Oh, all right. Very cool. Okay, it's not a quick assignment. That's true devotion. That's devotion. What? Oh, you just brought it with you?
That's what I emailed you from, but I fixed it.
Foreign country. Where were you? Mexico, Canada?
Bahamas.
The Bahamas? I have no... Yeah, it's fine. You should have had problems then, being in the Bahamas. Nice. Very cool. Okay, so the agenda today. We're going to talk about microcontrollers. I'm going to give a little talk about architecture. We're going to talk about a little bit of peripherals on a microcontroller, common usages. And then essentially we're going to jump right into Arduino sketches. If you've done Arduino sketches before, some of this will be review. However, I'm going to go into some of the more advanced Arduino commands. And when I say advanced Arduino commands, I mean the raw AVR C code that you can write on Arduino so that you can access things really, really quickly. One of the things that's great about Arduino is that you can write C code and people can read it and immediately know what the microcontroller is doing. And that is the biggest benefit of Arduino, is this rapid prototyping. The biggest downside of Arduino, which is just basically the programming environment, is it's not very fast. But you have access to all of the raw code that you can write for a microcontroller on the AVR. And we'll talk, if you understand none of the three-letter acronyms that I'm saying right now, you will. Okay, so an embedded system. A definition of an embedded system is a computer system with a dedicated function within a larger mechanical or electrical system, right? It's often with a real-time computing constraints, right? That is the definition straight off of a Wikipedia, Google, whatever, right? Which I guess would be Webster's Dictionary. So some examples of an embedded system would be a camera, microcontrollers, FPGAs. You guys work with FPGAs? Okay, no, you don't. None of you work with FPGAs. Wow. Once, okay. the Internet of Things, anything that's connected with home automation would be considered an embedded system. All it is you have a little mini computer, not a mini computer. You have a little embedded system that's controlling peripherals and architecture. So like your camera, when you click the button, it takes a picture because there's a small embedded system in it controlling all the peripherals on it. There's many, many things that were considered an embedded system. In fact, more things that work computationally right now would be considered an embedded system than you have desktop computers or laptops, right? Because this is essentially the age of mobile computing and the age of the Internet of Things, right? So let me ask you a question. What is this? That's a Raspberry Pi. What is a Raspberry Pi?
Awesomeness.
Awesomeness, not a definition. But I like the enthusiasm. A Linux computer built around a system on a chip. Is this an embedded system? It is. It is. It not can be. It is, right? It's got all of these peripherals that are connected on it, right? It's got an HDMI out so that you can watch video from it. This is an embedded system, right? It's this mobile embedded system, right? It's running Linux, which is a little weird for an embedded system to be running an operating system, but it's also a minimalist Linux that it's running. Right? It's not a real-time Linux or real-time OS, but that's okay. It's still an embedded system, even though it's got an OS. Typically, we don't have an OS on it. What about this? Is this an embedded system? Do you guys know what this is? The Nest? The smart thermostat? It is pretty awesome. How much did it sell for to Google? They sold this company?
4 billion.
1.2 billion. 4 billion? It's like a lot of money. A lot of money. Right? But it's essentially a smart thermostat. That's an embedded system. What about this? What is that? That's a home router. Is that an embedded system? You bet your bottom. Right? I'm on video, or I'd say something else. What is this? It's an Arduino. Is this an embedded system?
Yes.
Yes, I'm easing you guys back in from spring break, okay? Welcome back. All right. Is this an embedded system? Oh, I got people saying no. I got people doing this. I got people doing yeah. What is it?
You can argue either way.
You can argue it either way. You know what? That's probably the best answer I'm going to get today. I would argue that this is an embedded system, right? It's an embedded system. It is a full CPU running a full OS with dedicated sensors, with dedicated output. It can run user interface, right? So it's interruptible. All of the logic and everything that's built into this thing, I would say this is the best embedded system that was ever built. Not just the iPhone, just a phone, smartphone. Okay? So I think I would call this an embedded system. I think it's pretty cool. So the generic embedded system, what makes an embedded system different from a desktop computer? A desktop computer is not an embedded system because it's not embedded inside of really any other architecture around it, right? It's your desktop. I would classify, that's probably the only thing that I would consider not an embedded system, other than like a mainframe. Right? So typically an embedded system is going to have a CPU. You guys know what that is, right? Okay. Around the CPU, we're going to have a couple of things that are dedicated. These are things that are built in hardware, right? Which means they're etched into the silicon that's around the CPU. And we're going to have some reset logic for resetting the chip. All right. We're going to have some memory. We're going to have some peripherals. Right? Peripherals is just kind of the miscellaneous that's on the side of the CPU. But it's directly connected. It's right off of the CPU. When I say that, I'm talking about it's, nanometers away, micrometers away. We have some clock logic, right? Which means you have some kind of clock that's running very, very fast. Well, not that fast, maybe 32 megahertz. Right? You've got some logic that's built around that so that you can take the clock and go different places with it. How many of you guys have taken computer architecture? Is this looking familiar? Yeah. We've got some program memory that's right off of the side, and we have a bunch of timers that are connected in with a lot of control logic. Okay? Normally, if you want this to be useful, it's an embedded system, we're going to have an analog to digital converter. That connects to all inputs that are there. We're also going to have some digital connections, such as USB, serial, parallel port. I haven't seen a parallel port in probably 10 years, but that's okay. It's still on there. It's a digital input. And then we have, say, digital analog converters, right? So, or anything that kind of outputs, right? So things like LEDs, you can control an actuator. What is an actuator? Who knows what an actuator is? What? What is it?
We have like linear actuators for senior design that move forward back.
All right, so that's a linear actuator. An actuator is anything that converts an electrical signal into digital motion, right? Mechanical motion. Wow. Has been a long time, right? So your linear actuator, all it does is it moves something this way, okay? A motor, that's considered another actuator. Well, actually, a motor is a special thing. A motor is considered a motor. It's the one thing that converts energy into mechanical energy that's not considered an actuator. A solenoid. Who knows what a solenoid is? Your car has one. No? Yeah, basically. It's a little coil of wire, right? And it's got this little kind of arm in it. When you apply current to this, it forces that. It's a magnet. It forces it forward, pushes it out, okay? If you do that really, really quickly back in this way, that's a little, like a vibration motor where it's this kind of thing. That would be considered an actuator, solenoid. Okay. Everything in there right now that is not an input or an output, so this whole thing, this is a package deal. This is the most common thing that you would get with a microcontroller, which incorporates the CPU, all of the logic, a dedicated analog to digital converter, sometimes a digital to analog converter, a full digital analog converter. Most of the time we'll talk about how to do that though. And then it's got a bunch of buffers so that you can buffer the output, such as serial logic, SPI, I2C, TTL. Nope. I'm waiting for someone to just... Okay, fair enough. So we're good. We'll get into that. You guys are tough today. So the CPU, if it's on a microcontroller, a lot of times you'll hear this called an MCU, basically a microcontroller unit, right? And the reason that they call it that is because when we talk about a CPU on a microcontroller, it is so ingrained with all of the other peripherals that are on there. We have the ALU, your arithmetic logic unit, right, which is for doing all of the program instructions that we have that it can do in one clock cycle, maybe more. Right next to it, we have something called a register. What's a register? For those of you who take in computer architecture, or those of you who know anyway. A register. It's a type of memory, right? You can write to it, and it stays, and you can read from it. It's a very specialized type of memory, right? Because it's actually, they're pretty expensive to make a register, but it's extremely fast to read and write from. Okay? And they're right off of the CPU. Inside of a microcontroller, the registers control all of the operation, right? So when you go through the datasheet is nothing but here's the name of a register, here's what happens when you set the different bits in it. Each register is 8 bits, usually, right? And each bit controls something that the microcontroller does. Right? So if you set this specialized register, all of a sudden something starts happening, right? Because you've got all these peripherals that read those registers and then do stuff. It's all of the control logic for this microcontroller. You're going to have a control unit. Essentially, the control unit, most common one's the decoder, which is going in. It's helping the ALU decode instructions. And some cache memory that's usually on the side right there. It's very, very fast to read and write from. Okay? So there's your MCU. Okay, a lot of times you'll also have some special timing circuitry. So this is circuitry, so if you're running at 32 megahertz, there's some special logic circuitry to divide that down to 16 megahertz or 8 megahertz or, you know, a couple of kilohertz so that it can sit there and control other things that are on the microcontroller, right? So you got some specialized circuitry that's there. Okay, this is the Arduino, right? This whole board. That's the Arduino. A lot of times people will say that the chip on there is the Arduino, that is not an Arduino. What is that? What is that chip right there? That's the microcontroller, right? The Arduino, this Arduino is filled with lots and lots of things. All right, what's on the Arduino? Who knows what this is? That's the clock. That's a quartz crystal. It's running at 16 megahertz. so that it can sit there and feed that into the microcontroller. Otherwise, the microcontroller, it doesn't have an onboard clock, right? Or it does, but it oscillates really, really slowly. What is this? We have no idea, right? Right? There's lots of stuff on here that helps. What's that? Actually, I may have been pointing to a resistor when I pointed up there. I was just pointing to a random IC. Okay? I actually don't know what that is. It's probably a voltage regulator, which essentially takes, when you put some voltage, say, on the input of this Arduino, let's say you could put 9 volts in, it's going to regulate that down so that the board has 5 volts or 3.3 volts or whatever it runs on. And all of this circuitry there is usually just to help that out. This little chip right here on the very top, that helps it communicate with the computer. Essentially, it's a USB, right? So it's essentially all of the hardware so that this chip can just send off some, essentially some serial code, and it communicates back to the computer over USB, right? It's actually, there's a lot involved in that. That's why they have a separate chip. They want it just to run off chip. This is not low power, okay? It's great for prototyping on. This right here is the microcontroller. Everything that we do is programming that thing right there. And you can pull it off, except for the boards that I give you where it's surface mounted onto the thing. Okay? So that microcontroller, that's actually an Atmega 328. It'll run at 16 megahertz on the Arduino board. It has a 16-bit ALU, which means it does 16-bit integer operations, right, on each of the lines. Do you guys know what an ALU is when I say that? Some people do. Basically, it's the brain behind everything, right? You give the ALU an instruction, and it takes two or more pieces of data, 16-bit pieces of data, and spits out the result. Whether that's multiplication, division, addition, no ops.
What'd you say it stands for?
The arithmetic logic unit. All right? It has 2 kilobytes of SRAM. What's SRAM? Static RAM. It's memory. It's read-write. Yeah? There's 2 kilobytes. Think about that. There's 2 kilobytes of memory on this. That's not a lot. Okay? You can't do much with 2 kilobytes. The good thing is, there's no operating system running on this thing. You have a full 2 kilobytes to work with. Okay? There's nothing else that's eating up the memory in there. There's 32 kilobytes of flash memory. All right? What's flash memory?
Dynamic RAM?
It's not dynamic RAM, but it's long-term storage, right? Like my new laptop is, the whole hard drive is flash memory, right? It's essentially a hard drive. You turn the power off and you turn it back on, all the memory stays the same, right? It's non-volatile. There's 1 kilobyte of EEPROM. We'll get back to that. There's 14 general purpose input-output ports on this, which basically means digital inputs and outputs. 6 of those can be used for something called pulse width modulation, or PWM. Oh, and essentially those pins, can you guys see my mouse up here? Those pins are numbered 0 to 13 up here. Right, so those are the 14 GPIO. On the very bottom down here, you have A0 through A6. Those are those 6 analog inputs. So you have 6 inputs where you can measure and convert an analog value to a digital value. There's a hardware serial, which is connected on pins 0 and 1. This is TTL logic, so it's true like serial port. When someone says serial port, that's the de facto type. There's also a hardware SPI, which is a serial peripheral interface. It's basically another form of serial input where you can have multiple things connected. You have a master and a slave. Okay. Whew. That was a lot to go through. We're done. Let's go. No? All right. There's some really excellent tutorials for Arduino on Adafruit.com. Adafruit was created in 2005 by this nice lady that graduated from MIT. She decided that basically she wanted to create a business where she could sell a lot of things that were put together that connected really easily to an Arduino, and then put tutorials up for how to use each of those things that connect to the Arduino and make them really wonderful and great, and now she makes a lot of money. Okay? But those tutorials are some of the best you'll see online, and there's a link to them. Okay? We're going to go over how to use the Arduino. Okay, so when you open up an Arduino, this is open source. You can download the Arduino software. Okay, just go to arduino.com. And everything is written in C, and you're going to use this little IDE right here, which is the Arduino IDE. Essentially, you will use a bunch of Arduino functions, and you'll get intimately familiar with them by the end of this lab. So this is called a sketch. So let me just open one up. Okay. Here we are. Oh, not this one. This one. Okay, so here's some code to blink an LED forever. I think this is funny because when you're dealing with a microcontroller, most of what you're going to be doing when you're debugging is going to come down to blinking an LED to try and figure out what is wrong in your code. Okay? It's the easiest way to get access to a pin and look at what's happening or look at timing. Okay? So essentially, here's what I'm going to do. Everything that you can do in regular C code, you can do here. Actually, you can do C++ code in Arduino, but it's not considered Arduino-esque to write C++ because when you have classes, essentially you're using a lot of memory that kind of you don't want to. Even though it's not a whole lot, you've only got 2 kilobytes to work with. So when you create a class structure that's there and it's saving everything in memory, it's still eating up a lot of memory that you don't have on an Arduino. Okay, so you still can use it. It's absolutely fine. You just need to be aware of how to use it. So in this sketch right here, I've got a pound define and blink delay. So my blink delay is 500, and then I've got another pound define under my pin definitions, and that's 13. So pin 13 on this Arduino is tied to an LED on the board. Okay? Actually, can you guys see that blinking LED? Let me put it up here. See the blinking LED? That's coming straight. No? Oh. Sorry. That was a weird laugh. All right. My wife would have totally made fun of me. So here. So there's a blinking LED. All right. That is connected to pin 13. That's the LED that I'm talking about. Whenever you write out to pin 13, if it's a digital high, you're going to light up that LED. There's nothing you can do about it. Okay? It's really great for debugging. So let's go back here. So essentially, this is what this code does. You'll have this setup statement that's right here. This is something that when the microcontroller gets booted, this function and anything inside that function gets run. Okay? So I call this function pin mode LED output. What does that do? If you were going to tell me what that did, what did that do? Based on just what you see here for an Arduino. Is that readable code? I'm saying pin 13 is an output. That is it. Done. Why am I saying pin 13 is an output? Because I could also set it as an input. I could say, oh, I want this to be a digital input. I want to read from it and see if it's high or low. Now I'm just going to set it. It's a digital output, high or low. All right? So here's my main loop. This is essentially my operating system right here. It's my main loop. All it does, I do this thing called digital write on pin 13, and I make it logic high. I delay for 500 milliseconds. That's what this delay function does. I'm going to wait 500 milliseconds. I'm going to do digital write and make it low. And then I'm going to wait another 500 milliseconds, and this is going to loop back around and do it again. Okay? That is it. We made our first Arduino sketch. It's hello world. Now, up inside here in Arduino, I can go to Preferences, I can go to File. So I can go to File and go to Examples right here. And under Examples, you're going to have a bunch of different open source code that you can write for the Arduino. And just look at examples that people have written. This comes stock with Arduino. Okay? This is a great library. So basics. Oh, I want to do an analog read. I want the bare minimum. I want to blink an LED. You can see how somebody else did it. Okay? I want to read an analog voltage or fade that LED. All sorts of stuff in there that you can look at. Inside of Tools is where you'll need to specify which board you are using. So we are using an Arduino Uno, and you can see that that's the one selected here. Okay? There are also a bunch of different other Arduino boards that you can buy and use. We're going to use the Uno because it's cheap. It's $12. Or $30 if you buy the real one. The serial port that we're connected to is right here. That's just the serial port that this is on my computer. So this is hooked up over USB, and this is the serial port. I'm on 1421. Okay? If you're on a Windows machine, which you could do. If you're on a Windows machine, this would show up as a COM port. Okay? So now I can click this little thing up here, this verify button, and that will compile this code, essentially. Okay? So I do that. It says compiling the sketch down here, done compiling, and it says my binary sketch size is 1 kilobyte, right? 1076 bytes, right? Why is that important? Because we only have 32 kilobytes of flash on this thing, and that is where our program is stored. Okay? All right, so if I upload this to the board, what I'm gonna do is I'm gonna click this upload button and I'm gonna go right over here, see if you can see what's going on. Well, it uploaded, and now the LED is blinking again. Okay? Oh, whoops. Retry to upload with another serial port. Yeah. I didn't select the right serial port. Okay. Now upload. Whoop, whoop. Compiling sketch, uploading, done uploading. Okay. Good? Excellent. Okay. So called on startup or reset, run forever. If you're going to do serial port communication on the Arduino, it's really, really simple. Remember how I told you there was those RX and TX pins that are pins 0 and 1 on the controller? Those are exposed. You can use those for any serial port that you want. Those are also hooked up to the USB serial port. So I can write straight back to the computer using those ports. So if I were to do something like serial.begin 9600, that initializes the serial port on here to 9600 baud. What is 9600 baud? No? Really? Baud. It's 9600 bits per second that I can send on one line. Essentially what it does is it holds the line high, and then whenever it wants to transmit data, it will go low, and then it will start transmitting zeros and ones along that line, okay, in a specified manner. So it needs to know what frequency those bits are coming in at. It's 9600, so 9600 bits per second are what I'm sending on the serial port. Okay? So essentially I can do serial.begin 9600, and I will get a baud rate of 9600 pulses per second. Bits per second. Then, inside of my main loop, let's say I have this variable called resistance. I can say serial.print resistance, which is a float, and it will send that along the serial port in ASCII text. Okay? It'll convert this float over to ASCII, and then send it on the serial port. Okay? I can also send a string just like this, serial.print. Let's say, oh, this is my resistance in kilo ohms. So let's just do that really quickly. Right, so this I would do serial.begin 9600. Can everybody see this? Fair enough? Okay, so now every single time that I've blinked the LED, I'm just going to do serial dot print, and then I'm going to say LED blinked, like that. Okay? Wow. Actually, you know what I should do here? End line. That would be nice. I'm going to save. I'm going to upload this. Okay. Now, as you can see, if you can, there's a blinking LED up there still. But now, if I go, see this little button up here? It's a serial monitor. I'm going to click on it. Voila. LED blinked. Gets sent on the serial port in ASCII text. Everyone's happy? Try to do that on any other microcontroller in less than a minute and a half and see if it's that easy. Okay? The Arduino makes this really, really easy. Okay? You didn't even have to know what a serial port was to know how to work that, right? Okay? That's good. Right? Rapid prototyping means we can do a lot of other stuff. Okay. So, that was serial print. Okay, so let's get back to the specifics. So this Atmega CPU, as we talked about, it's a small ALU. The one that we have is going to be 16 bits. There are some out there, if you were to buy an Arduino, there's still some of the 8-bit packages, right? So it's an 8-bit ALU. The instruction set is RISC. You guys know what that means? Yeah? See, now we're getting into the computer science-y part of this, all right? Okay? That's right. It's a simple instruction set that's there. There's a little bit of redundancy to speed things up. This is a Harvard architecture. Okay, that means that there's separate program and data memory, which can be going on at the same time. So you can be doing something on the ALU and fetching memory for the new operation that you're about to come in. Right? That's a Harvard architecture. Almost every microcontroller uses it. And you got a pipelined load store, which means that you can read and write from registers, usually in one clock cycle. Okay, and you can do more than one at a time. It's pipelined for it, so you can read in register values. Again, low clock speeds on any of the Atmel type AVRs that are there, and any of the Atmel microcontrollers, you're going to have low clock speeds, somewhere between 8 and 32 megahertz. That's not very fast, but it's fast enough for most of the operations that we want to do because we're not running an OS. It is very much optimized for low-level compilers like C. However, you will still find a lot of people that want to program microcontrollers in assembly language. And the reason that they do that is to avoid any of those compile time operations, sometimes the optimizations, that bog this down just a little bit. So like a lot of times if you're running, say, an FFT on a microcontroller, it will be written in assembly code to make it just be as fast as possible. Right? So you call it and it comes back. Right? Normally, you can actually just like say pound defined ASM assembly and write assembly code right in the middle of C code and then say end assembly. Okay, and it'll be able to compile that and put it. And typically, there's not an operating system. Every once in a while, you'll see a real-time OS that's run, but it's increasingly not very popular. Use real time. However, embedded systems right now are right on the fringe of, okay, here's this microcontrollers that we're learning about, and then here are these Raspberry Pi type embedded systems that are running Linux. They're running an operating system that you can write Python for and put a script on and do a lot of things with them. I mean, the industry standard is kind of switching over to that, right? So you'll see things like Belkin has something called a Smart Module or the Wemo. That's all written. It's a Linux platform. Just things like the Raspberry Pi. They're all written in a Linux platform. There's something called the Firefly, which is in the industry standard. It's a microcontroller that runs Linux, right? The good thing about that is it's really easy to do things like networking, like TCP/IP from it, right? It's not that hard to do it from a microcontroller, but everybody knows how to work with an operating system, right? And so they're able to find programmers and put them in there and just have them run things and rapidly build a system, okay? So it's kind of 6 and 1/2 dozen of the other. Don't know what you'll see if you actually get a job working with microcontrollers or embedded systems. You might see this, and you might see OS. I'm assuming you know how to program in Linux, so you're good there. All right, memory. Memory is on this chip only. That means that when you buy a microcontroller, or the Arduino, the microcontroller it comes with, the memory that's on it, that's what you got. That is it. There's no RAM upgrade. It's limited, and there's no way to increase the memory on this. Usually, there are some microcontrollers that have some dedicated pins on them for when you'd want to do like SRAM access for an off-chip SRAM, right? So you could buy a chip that's SRAM, solder it down onto the board, and make sure the wires are connected, and then you set it up. Essentially, when you're loading up the program, you tell it which pins to go out on and read from the SRAM. Okay, that is not usually the way you want to do it with a microcontroller because it's a lot slower, and you have limited clock cycles anyway. The main difference in price comes from memory when you're buying microcontrollers. It's usually not what it can do, but it's the amount of memory that sits on it. So this Atmega chip that we have, it has 3 types of memory. And we talked about them before. You've got the SRAM, you have the EEPROM, and you have the flash memory, right? So the SRAM is volatile, right? And when I say volatile, what do I mean? You turn it off and it's gone. Yeah. Once you take power away from it, it's gone, right? Pretty simple. EEPROM and flash are non-volatile, so once you write from them, you turn the power off and you turn it back on, you can get access to all of that memory back. All right. So let's talk about the SRAM first. Let's dive in here. The SRAM is divided into 3 different areas, physical areas on the chip, okay? The first thing it does, all of your static and global variables that you write inside of the Arduino environment, those are written physically one next to another on the bottom of the SRAM, okay, on one side of the SRAM, right? All of that memory gets written, okay? And that happens right at when the microcontroller is booted up. So anything that you have declared as global or static gets set. You're going to have the stack, which is written on the other side of the microcontroller, physically, the other side. Those are going to be things like local variables, anything that's declared inside of a function, the name of a function call. Let's say you had like a pointer to a function and you were passing it around. That's all stored in the stack. And then you have the heap, which is all of your dynamic memory allocations, right? Right? So this is really, really kind of similar to what you'd expect on any, even if you had an operating system that was running. Okay? The one thing that's different here is you have a very limited amount of memory, right? So what happens if you use up the heap and you use up the stack and somewhere they start to meet in the middle, physically, in the memory? What happens? Boom! That's what happens. They do. They start overwriting each other.
Will the chip actually...
The chip doesn't have a clue. No, the chip will not explode. The chip has no idea that it is overwriting memory that it has set. It has no clue whatsoever. That logic is not built into the microcontroller. It's just going to start overwriting stuff. Maybe the heap is overwriting down here, all that kind of stuff. It has no idea. So all of a sudden, your chip starts behaving. You're going to come to me and be like, hey, it's behaving funny. I don't know what's wrong with it. And you're looking at it, you're like, all of a sudden it'll like reset itself and then it'll be fine. And you have no idea what's happening. You have no idea. And it's not telling you anything. Okay? It's extremely difficult to debug that has happened. All right? But it's worse than you think. Okay. So, remember I said this is not an operating system. The garbage collection on this for using your dynamic memory allocations is really, really primitive. And what I mean by that is this. You have your stack and you have your heap. Okay? So, I hope this shows up. So let's say you allocate some memory inside of the heap. Okay? And I'm going to denote those. Wow, this barely shows these very, very faded red blocks down at the bottom. Okay? You're allocating some of that heap memory. Okay? And maybe you allocate some more. Right? And then all of a sudden you look back at this and you're like, okay, I'm going to get rid of some of this that I pointed to. That right there. I'm going to get rid of that memory. I'm going to deallocate it from the heap. Okay? That's great. That's perfect. That is good programming practice. The problem is that the Arduino, when it's looking back at this, it has no idea really that that's been deallocated. The only thing that it knows is that there's other memory that's been deallocated or that's still allocated in front of that memory, physically, on the chip. Okay, so the next time you want to allocate memory, it stacks it on the top. And then maybe you do some more deallocations in here. right? And you keep allocating some more memory. Maybe you're really deallocating. Like you don't have 2 kilobytes allocated in the heap at all. You do this. Then what happens? Boom. All right? It will only free up that memory that you have if everything that you allocated after that, you also deallocate. Then it can start taking the heap down, the size. So if your heap is fragmented in any way, it'll blow up, metaphorically. So how do you avoid that? To avoid fragmentation, try not to use dynamic memory allocation. Seriously, right? If it's not necessary, try not to use it. So that's things like malloc, calloc, and realloc. All right? Try to stay away from those, right? Those are great programming tools, but they are not great on a microcontroller. Prefer local variables over global variables, okay? Because your global variables will be allocated no matter what. They are going to take up that bottom of the memory space, and they are there for good if they're declared globally. Also, a really good idea is to place any of your interim calculations inside of a separate function. And the reason that you would want to do something like that is because after any function call, that's when this is going to go through. It's going to look at all of the local variables, and it's going to release everything from the stack, right? And it's going to do it immediately and completely, right? So if you do that inside of a function call, you allocate, 512 things, you gather something through it, do that calculation, then you return. All of that gets released from the stack. Okay? Cleaned up. Okay. So if I wrote some code that looked like this, I've got temp sensor data at the top. It's 512. What part of this is bad? Malloc. Malloc is not good, right here. But this is probably still going to work because I'm not doing a bunch of dynamic memory allocations, right? However, with these 2 function calls, I've already taken up half of my SRAM. Okay? Everybody see that? I've got 2 kilobytes. I'm taking up a kilobyte. Okay. Good. This temp sensor data, if it's really temporary, allocate it somewhere else. Do it locally. Right? If I need to read in a bunch of sensor data, take the min or the mean or the maximum of that array and then return back without doing anything with that temperature, with that sensor data, then allocate it inside of a function. Okay. Non-volatile memory. Volatile. The EEPROM. EEPROM stands for Electronically Erasable Programmable Memory. Read-only memory. I love it. This was like when I was an undergrad. I always had a problem with the wording of EEPROM. I was like, it's an electronically erasable, programmable, read-only memory. Right, I was like, I would raise my hand, like I must have got on the nerves of every single professor that tried to tell me that it was okay that this happened. Anyway, so EEPROM, thing stays in memory when you turn it off, like we talked about. The only thing with EEPROM is you have a set number of writes and erases when you're dealing with an EEPROM. So on the Arduino, you have about 100,000 writes and erases that you can do on the EEPROM before you kill that memory. Okay? Basically, it won't be usable. Like you can write to it, and when you read from it, you'll get garbage back. Right? It's just not working anymore. You have an infinite number of reads from it, right? So it's really good for doing things like saving the state of the Arduino that you're in if you need to. If you know you're about to like run out of battery, you can save state and just wait for everything to turn off. When you do a write, every single byte that you're writing into the EEPROM takes about 3.3 milliseconds to write to. That's a long time. Okay? If you're running at 16 megahertz and it takes 3.3 milliseconds per byte to write to the EEPROM, it's an expensive operation and it takes a lot of power to write into. Okay? But it's the best place if you want non-volatile memory. Okay? So if you want access to the EEPROM, then you'll have to include this header called #include eeprom.h, and you'll need the address that you want to write to and the value that you want to write to, and you'll have to write it byte by byte. right? So if you have a float, you need to separate it out into the bytes that are afloat and write them in. So essentially, like, I'm going to write the values right here from 0 to 255. Essentially, what I'm going to do, I'm going to call this EEPROM.write, and I'm going to write this value to an address. So the address is a number between 0 and 511. Okay? So basically, you have half a K of EEPROM, a half a kilobyte. Okay? So that's address 0 through 512. And if you want to read from it, it's EEPROM.read, right? So it's a pretty easy library to use. Okay. The one thing you'll want to do here is, again, there's nothing that's protecting this memory, right? So if you want to write something to an address that's on the EEPROM, you want to keep writing across the entire EEPROM, right? So that you increase the life cycle of that EEPROM. So you don't always want to write to the first address. You just want to kind of go into it and write at different places. Is that fair? Yeah. Okay. And that's usually done for you. Like this right here, this is flash memory. It has a limited number of write cycles that I can do to it. However, they spread that out over the entire chip. I'm not always writing to like one physical location on the chip. It's spread out across the whole thing. Okay? You also have access to the program memory, the flash memory, right? So this is essentially where your code instructions are saved, right? So you have 32 kilobytes of flash memory that's on this microcontroller, right? And let's say you want to use that for more than just saving your instructions that you're writing on the microcontroller, right? So you can save things in it like strings or basically anything that you would have to store in the SRAM that you don't have to write to, right? So it's great for things that that you don't need except for, certain times. So essentially, I'm not going to go into a lot of this code here, but I am going to provide a link so that you can go onto Arduino's website reference. So you can click on that, and you can go over and see a bunch of different examples if you need to use the program space. I'm not going to go into it because I don't think you'll need this. But if you do need something to go into it, if you're really, really like working on space on your Arduino, this is great to have. Okay? Because you can't write to the location in program memory except when you compile the code. When you compile the code, it's going to write all of this into Flash, but you can read to it from it, right, when it's running. Okay? Does that make sense? You can only write to it during compile time, whenever you upload on the sketch, right? Okay. How are we doing? Oh, we're good. Okay. Let's talk about oscillators and a reset. So an oscillator is the clock to everything. It's that quartz crystal that we talked about on the Arduino board before. It is spread out and it goes all over the chip and it's divided down everywhere and it connects to a bunch of different control logic that's on your chip. You can control it externally if you want to. You could provide, you could take that crystal off and put another one on that's faster and things would still run. There's a lot of different resets that are on your microcontroller, and there's some really good reasons why that there's a reset on the microcontroller. There's this thing called a Watchdog Timer, which we'll talk about here in a second, and there's also this thing called a brownout reset. So these are two things on the microcontroller that essentially just reboot the entire microcontroller, right? And you can also reset the microcontroller on an interrupt. But what I want to talk about right now is the Watchdog Timer and the brownout reset. So a long time ago, not too long ago, in the 80s, when you were writing into a microcontroller, this is what you used to put on a satellite and basically shoot it out into space, okay? And so you would write all of this code on a microcontroller, and you would make sure that everything was running fine, but you could never test it under all of the different temperature and humidity scenarios that this thing was going to see on a satellite, all right? And so what would happen is they would program this microcontroller, they would debug it, they would make sure everything ran perfectly, they would launch the satellite into space, the microcontroller would get into essentially a place in memory where it should never have been somehow, somewhere, and that satellite was dead. All right? Millions of dollars, done, gone, out. So what they decided to do is say, hey, we're going to put this thing on it called a brownout reset. And all it is this hardware timer, this specialized timer, and it's going to sit there and count, and count, and count. And if ever that timer overflows, right, it gets to a certain value, I'm going to reset the entire chip. Okay? So essentially what that meant was that somewhere inside of your code, you had to disable the Watchdog Timer, right? So, or reset the Watchdog Timer, right? So you're running some things in code, you do some stuff, you reset the Watchdog Timer just to make sure it's like, hey, you know, this code is still running fine, don't reset the chip. Reset the Watchdog Timer and it would start counting up again, right? And you would go and you'd be doing stuff in your microcontroller, you'd reset the Watchdog Timer. So if ever you got into a place where you weren't supposed to be, the Watchdog Timer would just sit there and it would overflow, reset the chip, and essentially try and communicate back down to earth. All right? That's where the Watchdog Timer essentially came from. It's now used on every single microcontroller. And it's the bane of your existence. Okay? But you can disable it. So, this, you guys are taking digital logic? Some of you taking digital logic, some of you are in it right now. You really love it. All right? So you can read this diagram. So essentially, right down here is your Watchdog Timer. It's just sitting there. It's got an oscillator that's tied to it, and it's counting. Right? And if ever that gets to a certain value, bam, you get a logic 1 that puts on this. It goes into this. What is this? What is that? OR. OR. It's an OR gate. So if any of these happen, bam, this OR gate goes high. It sends a signal down to this delay. And then it also goes into this. Does anybody know what this is? It's a latch. It's a latch. Yeah. Now we're rocking this thing. We're good to go, right? So essentially, this goes high. It latches that value in, and it outputs the internal reset right here, okay? So it goes high, and it's going to wait until it gets reset by this. So essentially, this little delay counter down here, well, you'll see. It looks like this, right? So if this Watchdog Timer ever goes high for just a little bit, 1 clock cycle, that's going to latch that value in, and then this internal reset is going to go high for a long time until the chip resets. Okay? Everything gets rebooted. All memory that was in SRAM is gone. There's also this thing called a Watchdog Timer. So the brownout reset. The brownout reset is essentially something for when you're running on low battery. Okay? So when you're running on low battery, you've got this thing, VCC, that's the power to the microcontroller. Let's say it's 5 volts. That should be a constant 5 volts that you're getting out of it. When you got a battery tied to it, it can start to dip below 5 volts, right? And what you'll have is this. So you've got a load on a battery, and the microcontroller's working, everything's working fine, and the battery starts to die a little bit, and essentially it goes down, it dips down below 5 volts. The microcontroller will start to have things shut down on it that need to work on 5 volts. And when those things start to shut down, the load on the battery basically comes back up. And so the voltage on your batteries pops back up. And all of a sudden you've got power and everything starts to turn back on. And now that everything's back on, it starts to really pull the voltage down on the battery. And so when your voltage on the battery starts to get right on that threshold, the microcontroller starts just turning on and off. It just starts going nuts. It goes crazy, right? It can rewrite itself. It can undo code that's there. All sorts of bad things can happen when that happens. So there's this thing called the brownout reset, which it's looking at that voltage. And if that voltage ever drops below a certain value, it's going to shut down the chip. And it is not going to turn that chip back on until it gets to a higher voltage value than when it browned out. So essentially what that means is that you've got this thing called V bottom, VBOT minus, right? And so if your battery voltage ever drops below VBOT minus, you're going to get an internal reset. And it's actually not going to allow the chip to turn back on until you get to this other value, which is VBOT plus. All right? So that is 2 threshold values. That kind of thresholding is called hysteresis. Okay? What is that? What is that called? Hysteresis. All right, so we're good. Okay, so the Watchdog Timer. If you want to enable or disable the Watchdog Timer, you can do it in that setup function. So let's say you've got this little thing in here. It's called use Watchdog Timer = 1. Watchdog Timer enable, and then you're going to tell it what the duration of that Watchdog Timer should be. This right here, I've set it to 8 seconds. Right, so WDT 0 _ 8 seconds. Arduino understands that. It's fine. It's a constant. It's set to 8 seconds. You don't want to go much lower than that. Why don't you want to go much lower than that? Well, you don't want the Watchdog Timer to be really, really fast because you're not going to be able to program your chip. If you set the Watchdog Timer really, really low, essentially you're going to try and program the chip. The Watchdog Timer is going to start going off like this. It's going to get somewhere. It's going to reset the chip. And you'll never get it fully programmed. That microcontroller is now essentially dead. You might as well put a hammer to it. Okay? Don't go much lower than 8 seconds. Else, you can do this thing called the Watchdog Timer disable. Bam, it's right here. Okay? So, whenever you want to reset that value, you can do Watchdog Timer _ reset. It'll set it back down to 0, like we were talking about before. Okay? So, let's look at a quick example. All right. So, here's some code where I have a couple of things essentially pound defined up here. All that that really does is, let me show you. On the chip, on the side of the chip, I've got this little button right here. You guys see that? That button is connected between pins 2 and pin 4 on the Arduino, right? So I can click it, and it'll connect those 2 pins. All right? When I touch it and hold it down, it'll connect those 2 pins. Whenever I don't, those pins are unconnected to one another. Okay? So, and I've got that. I just took that button and just shoved it down into the Arduino. Okay? That's normally not there. So essentially, what I'm saying in here is pins 2 and 4 are where that button are connected. Okay? I'm using the Watchdog Timer, and I'm setting it to exactly that 8 seconds that we talked about. Inside of my main loop, I've got this thing that says if I'm on start, then on start = false. And I take this LED, I set it to high, delay for 1 second, and then I set it to low. And then when I get back into this loop, I'm not on start anymore and nothing happens. So whenever this thing first resets or starts up, it lights the LED for 1 second and then it's done. Okay? We'll talk about attaching interrupts, but essentially what I've got here is an interrupt that's connected to that button that I had. All right, so whenever I click that button, this function gets called, which is my Watchdog reset. Right? If I don't click that button, I'm going to go through, the Watchdog Timer is not going to be reset. Okay? So, let me upload this. It's uploading. It's done uploading. Okay, so now I'm going to wait for it to reset itself. Oh, there. It just reset. Did you see? This is what everything comes down to. Where's my button? Okay, so now I'll click the button. Oh, I didn't click it fast enough. Okay, let me click the button. No, I won't click it. No, I'll click it. It's like the worst job in the world. Did anybody watch Lost? This reminds me of Lost. No? Nobody watched Lost? You're laughing at me because I watched it? That's fine. All I was going to do is test out the Netflix streaming. That's all I was going to do. And that was the only thing available, was the Lost, the first episode of Lost. Man.
Today's the 10-year anniversary of the first episode.
Is it really? Now I feel old. Thanks. Has it really been that long? Man. It's all right. Season 4 sucked. All right. Here we go. Going back. Okay, so that was the Watchdog Timer. Any questions on the Watchdog Timer? We're all good. I want to move on to pulse width modulation. Yeah. Okay, so the Watchdog Timer, the real-time clock. We kind of talked about the Watchdog Timer. Pulse width modulation. Pulse width modulation is essentially some hardware. It's dedicated hardware that's on the chip that its only job is to generate pulses, which is essentially digital logic high, digital logic low, digital logic high, digital logic low, high, low, right there, okay? And its job is to generate a pulse width, right? So it's going to generate pulses. So let's say you're running at 100 hertz or something, right? If it's high for a very short amount of time, then that's called a small duty cycle square wave. A 50% duty cycle square wave would be this one in the middle, right here, right? Where it's high and low for 50% of the time, right? This right here is probably like a 10% duty cycle, right? So it generates a really, really thin width. Okay. And then this is like, I don't know, 95% or something, okay? This is useful in all sorts of applications, right? And we're going to talk about some of them. Essentially, let's say you had an LED that was tied to the output of this, right? Essentially, this would generate a very, very bright LED. This would generate a dimmer, and this would generate a really, really dimly lit LED, as long as these pulses were happening fast enough, right? So for the human eye, as long as you're going faster than, say, like 60 hertz, the eye is just going to see it as dimming. Okay? All right. And so there is dedicated hardware where you can set the width of these pulses in one clock cycle. You set it to a register, and then you do other stuff on the microcontroller, and it does nothing but generate those pulses one after another, one after another, one after another. You don't have to worry about it in code, right? So there's dedicated hardware to support that. So essentially, what you're going to do is you're going to set that register value, right? It's an 8-bit register value. And then you're going to have a counter, right? So the hardware has a counter that's counting from 0 to 255. After that, you have some sort of comparator that's sitting there. This counter is going up, and it's comparing to that register value that you set, right? The second that counter gets greater than the register value, it outputs logic low, right? Before that, it output logic high, right? That is the entire hardware inside of there for doing this pulse width modulation, right? You also actually, so this counter right here, the max value, that essentially controls the frequency of the wave that you're going to have, right? Because your counter is going to go until it gets to either, okay, 255 the max value, then it's going to go back down to 0 and start counting up again, right? If it goes to 1024 is the max value, right, then, well, you better have a 2-byte register, but it's essentially going to be counting up. Okay, and if it ever gets above this register value, that's when things change. Right? So this controls your frequency of the wave. The register value controls the duty cycle, right? Pretty easy. A low value, low duty cycle. High value, high duty cycle. Yes? Pretty good. The other thing that will control the frequency of this pulse width is the clock that you provide to the counter. Right? So you have a 16 megahertz clock. You're going to want to probably divide that down, right? To say like a 1 kilohertz that you're feeding into the counter, right? Why would you do that? First of all, do we know what pulse width modulation is? No. We're just controlling the width of that pulse, right? We're controlling the width of that pulse. And the way that we're doing it is by having a value and a counter. And all we're doing is comparing the value of that counter to the value that we've set here, right? If they ever get above each other, then we output high. And this just keeps repeating. We have this counter that's doing nothing but repeating, right? So if that counter can only go from 0 to 255, then I want to divide down the clock that I put into it, right? Otherwise, it's counting up at 16 megahertz, 0 to 255. And so this pulse width is it's just going crazy. Right? It may not even be detectable by some of the circuitry that we have. So if we divide that down to 1 kilohertz, then it's going to count from 0 to 255, and each of those, it's going to count up at 1 millisecond, right? 1 millisecond, it'll increment the counter, right? And so we can get this thing that's going up, and we get these nice pulse widths to come out. All right? Yeah, also controls the frequency, the divider that we put into the clock. So pulse width modulation. The reason that you would use this is for controlling like things like a servo or a motor. And when you're controlling that, the width of the pulse is everything when you're controlling a servo, and we'll talk about that probably next time. Okay? We'll talk about what a servo is in a moment and all that. Okay, so digital to analog conversion. This is how you do digital to analog conversion, is outputting pulse widths. Why? Well, essentially, you can output a square wave, and if you low-pass filter that square wave, right? If basically you low-pass filter it, you can turn it into a constant value, a constant analog value on the output. You don't have to know why that is, but just say, if you have, let's say you had essentially a really, really short pulse width, and you put that into a low-pass filter, on the output, you're going to get a value that's, say, small, a very small value, right? So think of it as kind of like a bathtub, okay? You've got a bathtub right here. This is my bathtub. And essentially what I'm going to be doing is and the drain is always on, right? So essentially I'm going to be filling this up with water, okay? And so each of those pulse widths is how much water I let fill into the bathtub, okay? But the drain is always letting that water come out, right? So it's slowly going down. I need to find the right amount. If I want the bathtub to be, say, this full, always, I need to find the right amount of water that I can throw into it such that it gets water, and it's constantly draining out here, and it's kind of staying right at one level. That's exactly what this does, right? So if my pulse width modulation is really, really large, I'm going to be putting in a lot of water every time and kind of letting it drain out. So it's kind of, there's a little more fluctuation in it, but I can kind of get an average that's pretty high, right? If my pulse width is really, really low, it's going to be back down here. That's what I'm doing. It's also, pulse width modulation is the way that you would control the brightness on an LED, right? So here's where the duty cycle matters, right? What we talked about before. So if you want to use the pulse width modulation on the Arduino, there's this wonderful thing called analog write, right? So essentially, it takes, the first value that it takes is the pin, right? So it has to be a pulse width modulation pin, right? What I mean by that is that dedicated pulse width hardware that we talked about, that has to be part of that pin that's there. So the Arduino has 6 of them. So on this Arduino, you'll notice there's this little thing called PWM. Well, anyway, all of the pins that are on there, those 0 through 13, if they have a little asterisk, a little tilde next to them, that means that they can be used as pulse width modulation outputs. They have the dedicated hardware in there. Okay? So essentially, I'm going to tell it which pin to write to, and I'm going to tell it the value, 0 to 255. Okay? And that's going to control the duty cycle of that pulse wave on the output. Right? 0 is basically going to be nothing on the output. 1, it'll be a very, very quick spike, right? 255, it'll basically be high the whole time. Is that okay? Yeah? All right. So what does that look like? Here's my pulse width modulation output. So essentially what I'm going to do here, I'm going to define, here's my LED. It's on pin 13. Now, that's the LED that's connected on my board, right? The problem with that, it's not a pulse width modulation output. Like, oh, okay, fine. So what I'm going to do is I'm going to take a wire, and I'm going to connect it from pin 11 to pin 13, right? So pin 11, pin 13. So now pin 11 is also going to be controlling that LED, right? So if I put digital high on pin 11, the LED will light up, okay? And I'm just going to turn pin 13 off. I don't want it to even deal with anything. So that's what this does right here. All right, so my pin mode, LED, I'm going to set the LED pin, which is pin 13, as an input. That basically turns it off, so it doesn't try and drive that LED. Right? Pin 11 is now going to be my output. So I'm going to do this. Okay, so I'm going to say if my LED brightness equals 0 or LED brightness equals 255, I'm going to change delta. I'm going to multiply delta by -1. Right? I'm going to say times equals -1, right? Then I'm going to say LED brightness plus equals delta. Okay? So I'm just going to count this LED brightness up from 0 to 255, 255 to 0. It's going to do this. Okay? Then I'm going to analog write to my pulse width modulation pin, which is pin 11. right there. And I'm going to tell it the brightness to spit out, right? So what is this going to do? What's it going to look like? Let's find out, right? And then I'm going to delay for a second. I'm going to delay for 10 milliseconds. So let me upload this onto there. Done uploading. Can you guys see that? It's fading, fading, getting brighter, fading. Okay? So that's the visual analog of the pulse width modulation pin. And that's the easiest way to use pulse width modulation. Okay? Very, very easy on the Arduino. Problem is, it doesn't give you a whole lot of control over the pulse width modulation that's there. So let's talk about how to get a little more control.
Why did you have to do the wire thing?
Oh, the wire thing? So pin 13 is a digital, it's a general purpose input output, but it doesn't have that pulse width modulation hardware on the chip, right? So I can't do that thing where I just like set the comparator value and then let the counter and stuff do its thing.
So there's not an LED hooked up straight to 11?
No. That's why I just took that. So all I did was I took the wire from pin 11 to pin 13 so that I could control that LED. I could have also taken an LED and stuck it in there and then took a resistor to ground and controlled that LED, right? If I wanted to. But we might as well use what's on board, the Arduino. What? Wait, no, that's not what I wanted to do. Great animation. Thanks, guys. Okay. Okay, so pulse width modulation. So essentially, I talked about that digital analog converter with the bathtub. All right, you can do a lot of stuff with that, and actually, you can do a whole lot of stuff with it. How are we doing on time? Oh, we are good. So essentially, this is the output of an oscilloscope. Okay, what is an oscilloscope? This is the output of a voltage monitor, right? And all it does is it monitors the voltage on a pin, and it displays it on the screen. Okay, so what I've done here is I've connected one of the probes that looks at the voltage onto the output of, say, one of my pins on my Arduino, right? And this is a pulse width modulation pin, right? So I'm going to look at all of the different pulses and the different pulse widths that it has. I've also connected it after a low-pass filter of this right here, okay? A low-pass filter is actually just a capacitor and a resistor, okay? Really, really simple. You have no idea, and you don't have to know what that is. All you have to know is it smooths it out, all right? Good. So essentially what happens here is I'm actually generating pulses, and I'm varying the pulse width that I'm outputting right here, right? So essentially I start at 10% duty cycle, right? The next pulse is 15, 25, 35% duty cycle. Do you guys see how it's getting bigger and wider? I get to 50%, 75, and 85%. 95 and then 100%. And then I leave it high for a little while and then start spreading those pulses apart. After I've low-pass filtered it, I get this bad boy. What is this? It's a sine wave. Yeah, you guys are back. So normally pulse width modulation defines a constant duty cycle spike, but if I vary that spike, I can get a time varying duty cycle like this, and I can create this awesome looking sine wave on the output. I can create any analog output that I want by using these pulse widths and smoothing them with my bathtub. All right? Cool. What does this code do? Let's see. For int analog value equals 0 to 255, analog write it and delay 10 milliseconds. Then from 254 to 0, decrement it and delay.
The same as the blink. Example where we try to go up.
It is. It's the exact same as the blink. If I were to look at that on an oscilloscope, what would I see? Wait, do you guys know what it's doing for the first off? I'm starting off with a small pulse, and I'm getting bigger and bigger and bigger, and then I'm taking it back down, right? So if I was hooked up to an LED, it'd be getting brighter and brighter and brighter, and then it would start fading, right? But what would that look like on my little oscilloscope out here? Any idea? If I smoothed it out. It's not the same as the sine wave. Yeah, the triangle. It's a triangle wave, right? It's just linearly increasing like this and then linearly decreasing. Okay? That was just a gut check to see if you guys were following with me. Is that okay? All right. Basically, this analog write is expecting a digital to analog conversion. So if the analog output is, 120, then it's going to try and output that analog value. Right? So 0 to 255 would be 0 to 5 volts. 120 is somewhere in between. So it's going to be somewhere, it's going to be like, I don't know. 120 is 2.5 volts or so. Right? This is what it's going to try and just output constantly. Right? Okay. So, yeah, we've got time. Pulse width modulation. No, we don't have time for this. I'm going to go through part of this, and we'll just stop when we get to the end. Okay, so this right here is non-Arduino code. This is what you normally write code, and this is what it looks like when you normally write code for a microcontroller. What does this code do? No idea. When you write code and you're setting registers on a microcontroller, if you don't have the data sheet right next to you and you're not constantly referring back to it, you don't have a clue what this code does. This code sets up 2 different pulse width modulations on different pins and sets up their duty cycle and sets up their frequency. And it does the whole thing by setting registers. Okay, so there's this register on the chip called TCC-R2A. There's another register called TCC-R2B. And then you see this little macro function, which is _BV, right? That little macro right there is essentially setting a bit. Okay, so this is a 8-bit register, and it's say, okay, well, inside that 8-bit register, I want the COM2A1 bit to be high, logic 1. I want the COM2B1 bit to be logic high. I want the WGM21 bit and the WGM20 bit to be logic high. What that does, no idea. Right? Actually, I do, but here. So set bit with this name in this register. So here is TCC-R2A. It is a timer counter control register. So timer counter control register A. That's what it stands for. All right? So it's 8 bits right here, and each of the bits that we can set inside there means something for the logic of this microcontroller. And the same thing with TCC-R2B. All right? So let's figure out what this does. Okay, so when I set this COM2A1 bit, then it turns out this is what happens, right? I go into the data sheet, which is somewhere like 300 pages, and I go search for what this does. So COM2A1 is set, and COM2A0 isn't mentioned here, so it's 0. Right? So if I set 1 and 0, what that says, oh, I'm going to clear OC2A on my compare match when up counting. What? This thing reads like stereo instructions. Okay? This is why Arduino is really, really nice to have. Okay? Essentially, this is what happens. You've got a counter that's called tcount2. It's one counter on the chip called tcount2. It starts counting up, and it's got this OC2A output, which it's going to compare to a value. Essentially, when OC2A is the output, all right? It's a register it's a bit that's getting set or cleared, right? So this bit, it's set when I'm up counting, and then whenever I pass a value, it gets cleared. And it's 0. Then when my counter resets itself and starts counting up, I'm going to set the OC2A bit, clear it, right? What is that? It's pulse width modulation, right? It's clearing and setting that bit. Same thing for COM2B1. Here's OC2B. This is another pin that I'm connected to. That I'm gonna clear OC2B whenever it matches some comparison. And then I'm gonna set it when I'm at the bottom of the counter. So set, clear, set, clear, set, clear. We're done. Okay, we'll talk about this next time on what these 2 bits do, and we'll get through the rest of microcontrollers next time. See you guys.